Okay, now moving into acids and bases properly, we need to first of all be able to do for all these different equilibriums an equilibrium constant. So in this case, for instance, HF, a weak acid, it's the same products over reactants. Now in every case here, water is aqueous, not a gas, or anything like that, and it's a constant, so it's not included. And it's the same products over reactants. Now the general constant Kc for equilibrium, we just changed to become Ka because it's an acid. So it's Ka, A for acid, and we'll have products over reactants, so it's F minus H3O plus over HF. Again, for this one, it would be Ka equals, oops, sorry about that, NH3, H3O plus over NH4 plus. Now, these next two aren't acids. Ammonia is a weak base, and so we don't call it Ka, we call it Kb. And it's going to be NH4 plus OH minus over NH3. And the last one's also a base, so it's going to be CH3COO minus. So that should be plus OH minus there. OH minus over CH3, and that should be plus there, CO3COOH, and that's CH3CO minus. Okay, so the equilibrium constant Ka or Kb should be relatively straightforward to do. Now there is a relationship, for instance, if you notice NH4 plus and NH3, it's a conjugate acid and base pair, and the relationship is that Ka times by Kb equals 1 times 10 to the negative 14. So if you know the Ka value, the equilibrium constant value for ammonium, that automatically is telling you the Kb value for NH3. All you have to do to work it out is go 1 times 10 to the negative 14, and that's what you enter into your calculator. You do not enter 10. You divide that by the Ka value, which is given, and in this case, for instance, if it was, 5.8 times 10 to the negative 10, that number would go in there, and when you divide that in there, that would give you your Kb value. The reason this is important is because generally you're only given Ka values, and you need to be able to use Kb values at times, so you need to be able to move between the two. Okay? Okay, now these are just Ka values, and they're a constant at a set temperature, just like any other equilibrium constant. They don't have a unit, but you should have some feeling for what they mean. Now, this one here is much larger, and what that tells you is that in this reaction with water, dissociation reaction, is that it dissociates more than the other two. So we're going to get more products, the equilibrium would lie more to the side. Now you can see this is a small number anyway, so it's all relative. Compared to the other two, it's just bigger. So this would be the stronger acid, although it is weak. It is a weak acid. This is a comparative thing. This would be number 2, and this would be number 3. Okay, so it's important to have some understanding of what these numbers mean. Now, as you can see, these numbers are a little bit troublesome, just like hydronium concentrations. And just as in pH, we've developed pH to make an easy comparison between different acidities. We do the same thing. So if we go minus log Ka, we get something called pKa. So I can go ahead and do that just the same as if you were pretending that was a concentration of hydronium ions. So So you enter log 2.9, it's minus log 2.9 exponent negative 8, and that's 7.53. So that first one, 7.53. The next one, log minus log 2.78 exponent negative 11, and that's 10.5 or 10.6. And then lastly, log 1.8 minus log 1.8 exponent negative 4, and that's 3.75. So remember, if we go back a little bit, this is the stronger of the acids, this is next, and this is next. And what we see is that the stronger the acid, the higher the Ka value, and therefore the lower the pKa value. So this is just like pH, where the higher the hydronium ion concentration, the lower the pH. So you should be able to discuss that, and discuss it relative to the equilibrium, that if you've got a higher Ka value, there's going to be more products, more hydronium ions, and therefore the Ka value is going to be higher, and that's going to reflect in a lower pKa value. Okay? Now, just one final thing, you should be able to switch between the two. So, if you're given a pKa value, you should be able to go back to Ka. Okay? So if you were given a pKa of 8.9, to go to a Ka value, you would just go inverse log. Now, inverse log is just the same as pushing shift log on your calculator, minus 8.9, remember there must be an minus there, because it was minus log to get that, and that will give you your new value. So if I just do that on my calculator now, shift log minus 8.9, I get 1.26 times 10 to the negative 9. Okay, and if I wanted Kb, it would just be a matter of 1 times 10 to the negative 14 divided by 1.26 times 10 to the negative 9, because that's effectively Kw divided by Ka. So let's have a look. 1 exponent negative 14 divided by 1.26 exponent negative 9, that equals 7.94 times 10 to the negative 6. So from that you can gather that if you are given pKa, you can work out what Ka is. And if you know what Ka is, you can work out what Kb is. Okay, because 1 times 10 to the negative 14, which is Kw, equals Ka times Kb. Okay, that's for conjugate acid-base pairs. So if we're talking about, for instance, the Ka of NH4+, we can work out the Kb for NH3, the conjugate base. These are important calculations that you can do, that you should be able to do.